Hello everyone, welcome to the Spintangle. Today I am here with a new topic, and this one is a lecture 5, I think so. This one is a lecture 5 of statistical mechanics. Okay, not sorry. This one is the lecture 4, I think so. The lecture 4 of statistical mechanics, in which we will be discussing distinguishable particles and indistinguishable particles, a very important topic of statistical mechanics. And from this topic we will know much more about microscopic world and its macroscopic reflections. Okay, so let's start with distinguishable and indistinguishable particles. So in statistical mechanics, we deal with two types of particles. One is classical particles and others are quantum particles. Okay, the classical particles are called distinguishable particles, and the quantum particles are called indistinguishable particles. Okay, let me start with one thing, that what is distinguishable particle and what is indistinguishable particle. From the context of our lives, from the context of everyday life, what we can see that, let me draw something. This is an interesting example. Okay, I think there will be an interesting example. Okay, say this is a box, and this box have some ports inside. Okay, and fill up the box with different color inks, different color balls. Say in this box initially we have a red ball, in this box initially we have a green ball, in this box we have a violet ball, and let me choose an ink. In this box let us consider that there is a yellow ball. Okay, if we do not shake the box, the entire box, these are the internal compartments. Okay, if we shake the box, and after shaking, what can happen here? The red ball can go this way, the green ball can come this way or this way. Okay, but you can, after shaking, and also before shaking, you can easily distinguish which particle goes where. Okay, initially say on this box, this one is the box 1, box 2, compartment 1, compartment 2, compartment 3 and compartment 4. This one you can easily say, after shaking, the red ball can go to 2, red ball can go to the compartment 2. Okay, the green ball can go to the compartment 3, suppose the yellow ball can go to the compartment 1, and so on, and the violet ball can go to the compartment 4. Okay, this is called distinguishable particles. A distinguishable particle can easily be distinguished from a set of particles. Okay, there are 4 particles. These are the 4 particles. This one, and this one. There are 4 particles. Okay, there are 4 particles. Okay, these are the 4 particles. you can easily distinguish them even after shaking the box. Okay, this is the property of distinguishable particles, that if there is a shaking or there is a if there is a excitement in the system, you can easily distinguish the particle even after the excitement produced. Okay, in case of indistinguishable particle, let me draw again the box here. Okay, let me fill with what are indistinguishable particles. Indistinguishable particles, you can say that this is this and this. These are four indistinguishable particles. Why these are four indistinguishable particles? Because you cannot distinguish as this one is number one particle. You cannot say this one is number one particle. Okay, initially you can say say consider that initially these are the 1 2 3 4 5 sorry 1 2, this is 3 and this is 4. These are the particle you can say initially. Okay, this one is the compartment 1, compartment 2, compartment 3 and compartment 4. After shaking, after producing an excitement, the system remains unchanged. The system remains unchanged. That you will also see that this is the state of the system even after shaking. Okay, this means you cannot say that the number one particle, the number one leveled particle goes where. You cannot say this one is what, this one is what, this one could be 1, could be 2, could be 3, could be 4. Okay, this is the probability this is the property of indistinguishable particles, in which you cannot distinguish the particles individually even after shaking or even after producing an excitement on these particles. Okay, I think this is clear to you. Okay, now let me write some properties. Okay, distinguishable particles, please give an heading. Distinguishable particles. What are distinguishable particles? Distinguishable particles are the particles having distinct wave functions. Distinct wave functions. Okay, what does it mean? Distinct wave function means, say the red particle was given, the characteristic wave of the red particle look like this. Okay, and in case of the green particle, say this is the green particle, and the wave look like this. This is the property of distinct wave function. You can easily distinguish what is which one is the wave function of red particle and which one is the wave function of green particle. This is shy red. Okay, this is shy green. Okay, this is the part. This is the first property of distinguishable particles, in which we say that distinguishable particles have distinct wave functions. Okay, now let me write the second. These wave functions are not overlapping. These are not overlapping. If these goes overlapping, if these are overlapping, then you cannot even if say there is 1,000 number of particles. Okay, there is 1,000 number of particles which are distinguishable. If the characteristics wave of each particle, this is the wave of, say, first particle, this is the wave of second particle, this is the wave of third particle, okay, this is the wave of fourth particle, this is the wave of fifth particle, and so on. After 1000 particle overlapping of the wave function of 1000 particle, you cannot distinguish which was the wave of first particle. You cannot distinguish. Okay, this was the second property. Okay, let me write the third property. Very important property is the third property. Okay, they do not obey Heisenberg's uncertainty principle. Okay, what is Heisenberg's uncertainty principle? That delta px dot delta x greater than equal to h cut upon 2. This is only valid for subatomic world. Okay, subatomic world. Okay, as the distinguishable particles are the particles of classical world. Wait for a while. Classical world. That means this will not surely obey this Heisenberg's uncertainty principle, because Heisenberg's uncertainty principle is strictly on the basis of fundamental quantum mechanics. Okay, this was the third property. I am not going more deep on the theory of Heisenberg's uncertainty principle. We will discuss in the quantum mechanics lecture. Okay, if you have any query about quantum mechanics lecture, then you can comment on the comment box below. I will try to give some video about quantum mechanics. Okay, next property, we can determine the position and momentum precisely at the same time. This resembles with the Heisenberg's uncertainty principle. Okay, not resembling, this is the reflection of the Heisenberg's uncertainty principle, that in classical world delta px becomes 0. That means there is no uncertainty in position. This means momentum is, what? Momentum is certain, and also delta x is equals to 0. This means position is certain. These two things violates the Heisenberg's uncertainty principle. So the property 4 is the reflection of property 3. Okay, in say in case of property 3, you can say if this is 0, then delta x will be what? This will be infinity. This happens in which place? This happens in Heisenberg's uncertainty principle. Okay, in classical world all things are certain. Position is certain, momentum is certain, and that means there is no uncertainty. These are the uncertainties. Deltas are the uncertainties. Okay, these are the uncertainties in momentum and position. Okay, let me write the property, fifth property. We can label the particles individually. Why? I have given this idea on the very initial of today's lecture. Okay, you can label this is what, this is the particle 1. You can easily level the particle 1. This is the particle 2, this is the particle 3, and this is the particle 4. Okay, let me write it here. Say you can easily level that this is the red ball, this is the red particle. Okay, you can easily level, you can easily level what is green, this is the green particle. Okay, green particle, that means the particles can be leveled individually. This is the fifth property. Okay, the sixth property is we can call them localized particles. Localized particles. Okay, what are the localized particles? Localized particles means you can easily give the particles a position. Say this is position x1, this is position x2, this is position x3, and this is position x4, and so on. Okay, you can place the red particle, you can place, this one is not right red. Okay, you can place the red particle in the position of x1. You can place the green particle in the place of x2. You can place the violet particle in the place of x3. You can easily localize the particle. This is the localization of particles. Okay, this is possible because they are distinguishable. You can easily put a particle and easily replace this particle to another place. Okay, easily. But in case of indistinguishable particles, it was not possible because say there were 4 same particles. There were 4 same particles. You do not know, if you close your eyes and you have to choose any one of them, you cannot say that you have chosen which particle. Please close your eyes. Okay, close your eyes, and you are supposed to choose any one of the particles. Then you can easily say that uh, which particle you have chosen is, you are not certain about the particles, which one is the number 1 particle, whether you have chosen number 1, whether you have chosen number 2, number 3, number 4, because all the particles are indistinguishable. Okay, they cannot be distinguished by any way. Okay, this is the sixth property. Okay, let me check one thing. The property, now the property 7. What is the 7th property and the last property? This one, I think so. And all other properties are relevant to each other. Okay, these are the basic properties for a 2 particle system. The total wave function will be written as this one is the composite wave function. This is called the composite wave function. Psi is equals to what? Say psi a1, psi b2. Okay, this means what? Particle 1 is in state A. Say this is the particle 1 is in state A. These are the 2 states. Suppose these are the 2 states. This one is the state A, this one is the state B. The particle 1, say this is the particle 1 and this is the particle 2. Okay, this is the particle 2. This is particle 2 and this is the particle 1. Particle 1 in state 1, this is in state 1, and particle 2 in state 2. Okay, okay, this means that particle 2, sorry, is in state B. The particle 2 is in state B. They are composite. Okay. A question. Okay, not this is not important. Okay. Now let's start. What are called indistinguishable particles? What are called indistinguishable particles? Okay. Let me change the ink first. Okay. The particles. This can be treated as the property 1. Okay. The particles having overlapped wave function are called indistinguishable particles. Indistinguishable particles. Okay, this is the first property. You can easily see that this one is the particle 1 and this one is the particle 2. Suppose the particle 1 has wave function, wave like this, and the particle 2 has wave like this. Okay, suppose when you close your eyes and you do not know which one is the particle 1 and which one is the particle 2, then how can you determine that which one is of the particle 1 and which one is of the particle 2? You cannot determine. Okay, because both are same colored. You can say both are same color. This is called indistinguishable particles. You cannot. I have told here the wave function. These wave functions are looking separate, but in case of indistinguishable particles, the wave function are overlapping in very higher way. They do not they do not be separated from each other. Okay, they do not be separated from each other, and even this is not the right way to represent the overlapping wave function. It is just an illustration. Okay, it is just an illustration that what is the wave function of. Okay, this is the wave of the particle 1, yes, and this is the wave of particle 2. These are same looking. Okay, these are same looking because in case of 100 or 1000 particles, 1000 indistinguishable particles, you cannot be you don't be able to distinguish the particles wave function as individual. Okay, okay, in the property 2, they obey Heisenberg's uncertainty principle. Okay, this is the important thing here to look at. Okay, they obey the Heisenberg's uncertainty principle. Why? Because indistinguishable particles, which are indistinguishable particles, say electron is an indistinguishable particle. Electron is an indistinguishable particle. This means a system of 2 lakhs electrons is a system of quantum particles. Okay, is it because electron is a subatomic particle, and it is because it is a part of the atom, and in case of subatomic particles we are able to introduce the Heisenberg's uncertainty principle. Okay, this is why the indistinguishable particles obey Heisenberg's uncertainty principle. Okay, now go back to the now go to the third point. Okay, we cannot we cannot determine the position and momentum of the particle. Sorry, let me I have forgotten this. Okay, sorry. We cannot determine the position and momentum of the particle at the same time. This means there is a uncertainty in position and there is a uncertainty in momentum. This means there is a, and this indicates us to introduce the Heisenberg's uncertainty principle. Okay, that if Heisenberg's uncertainty principle is what? Delta x delta px greater than or equal to h cut upon 2. Okay, this means what? If delta px is not equals to 0 and also delta px is finite, then what will happen here? Then delta x is also be not equals to 0. You can check it from this, that you can write it delta x, this means you can write it delta x equals to h cut upon greater than or equal to h cut upon 2 delta px. If this term, if this delta px is a finite and non-zero term, then you can easily say that delta x has to be finite and also non-zero. Okay, and also delta x is finite. This one is the third property and a very important property. Sometimes in case of competitive examination, you could be asked for these kind of properties. In case of conceptual questions, there can be some questions that are from these kind of concepts. Okay, now the property 4, they are non-localized. They are non-localized. This means they cannot be localized at some point. Okay, this is x1, this is x2, this is x3. This is okay, this is the property 4. Property 5 is what? We cannot trace the trajectory of the particles. Okay, now let me go into more deeper point of indistinguishable particles. Okay, what are the indistinguishable particles? Indistinguishable particles are of two types. Okay, these are quantum particles. Obviously these are quantum particles. These are of two types. One is fermions and the others are bosons. Okay, the fermions are the particles which were introduced by the eminent scientist named Enrico Fermi. Also, you know, an unit of Fermi, unit of what is 10 to the power minus 15 meter is called Fermi. Okay, this is in the name of Enrico Fermi because Enrico Fermi was a nuclear physicist and the nuclear, you know that nuclear radius is of the order of 10 to the power minus 15 meter, that is of Fermi order. Okay, this is why this is called fermions. And what are the bosons where the particles proposed by Satyanath Bose and Einstein. Satyanath Bose is a Bengali scientist, and in Bengal we used to call him as Satyendranath Bose. Okay, uh, in the international scientist community, Satyanath Bose was an underrated scientist, and um, bosons were the particles proposed by Satyanath Bose. You know about one thing, that Higgs boson. I think you have heard about Higgs boson. Higgs boson was the particles theoretical particle was the theoretical particles proposed by Peter Higgs, and these bosons, we are proud of this boson because this boson was first introduced by Satyanath Bose. Okay, he is, first of all, Satyanath Bose is an Indian scientist, and uh, and secondly, he is a Bengali scientist. Okay, fermions. Let me change the ink. What are fermions? Fermions have half or odd integral spin. Half or odd integral spin particles are called fermions. And what are bosons? Bosons have integral spin. Because the fermions are the particles like this. The electron is a fermion, say, proton is a fermion, even neutron is a fermion, and so on. Okay, these are the particles having spin angular momenta of about of h cut by 2. Spin angular momentum, this is the value of spin angular momentum of an electron, proton, or neutron. Okay, this um, this is not splitted, this is the real value of spin h cut upon 2. That spin, we used to say that electrons has spin up and spin down state. Spin up state is given by plus h cut upon 2. Spin down state is written as minus h cut upon 2, but the modulus of the spin angular momentum is given by h cut upon 2. Okay, and the bosons have integral spin, say photons, say Higgs bosons, say gravitons, the particles the which are carrier of gravity. Okay, gravitons and so on. These particles have integral spin, say h cut, 2 h cut, 3 h cut, 0. These are bosons. But fermions have odd integral spin. This means fermions can have h cut upon 2 as a spin value, 3 h cut upon 2. This means 1.5 h cut. Okay, so 5 h cut upon 2, 7 h cut upon 2. Okay, whatever it is. Never encountered more than 3 h cut by 2. Okay, these are the fermions. Okay, let me clear it. The fermions. Here comes the interesting point, that the total wave function for a fermion is antisymmetric. The total wave function for a fermion is antisymmetric. I am elaborating it. First, let me write the total wave function of a boson is symmetric here. Okay. Now let me elaborate this thing. What is total wave function? Total wave function is written as, let me write it clearly. Total wave function is written like this, that psi total, you can write it psi total as psi spatial, this means space part, and psi spin part. Okay, this is the spin part. Okay, this is the spin part, psi spin. This is the spatial wave function. This is called the spatial wave function. You can write it on your copy. And this is the spin wave function. Okay. The total wave function has to be antisymmetric in any way. In any way. In case of fermion, psi total is equals to is psi total is antisymmetric. Okay. In case of bosons, psi total is what? Symmetric. This means one thing, that say in case of fermions, psi spatial is symmetric, then psi spin has to be antisymmetric. Has to be antisymmetric. Why this is? Because to make the psi total antisymmetric. Psi total antisymmetric. Okay. The psi spatial, if psi spatial is symmetric and if psi spin is antisymmetric, then they are then multiplying them, we will get an antisymmetric wave function. This means in childhood we have learned about that the multiplying -1 with +1 gives -1. Okay, and negative positive becomes negative. Okay, positive negative becomes negative. Okay, -1 +1. Okay, you can write it like this. This is quite similar like this. If psi spatial is symmetric, then you can say this is a this can be labeled as +1. Suppose I am writing this. This is not the right notion. Okay, this is right. This is -1 because this is antisymmetry. Antisymmetry is given by -1. Okay. Now multiplying -1 with +1 with -1, what gives us? This gives -1. This means the total wave function is -1. This means antisymmetric. Okay. This is what I want to mention. This is -1. Okay. So let us write the wave function psi total in case of psi total. In case of fermions, becomes 1/√2. This is the normalizing factor. Okay, this comes to make the total probability 1. Psi A, psi 1, psi B, psi 2 minus psi A 2, psi B. This is the total wave function. Okay, this wave function is written in this way, that psi 1 2, psi total 1 2. You can write this thing. You can write this thing as psi total 1 comma 2. Okay. Now this comes from the exchange particle property, that if you flip the particle 1 and particle 2, if you flip, say the particle 1 is in this is the particle 1, this is the particle 2. If you exchange these particles, then what happens? Then happens that psi total becomes psi total 2 1 in case of Fermi. This is the wave function in case of Fermi particles. Okay, psi 2 1. This becomes what? 1 upon root 2 will not undergoes a change. Then therefore we can easily say that psi A becomes 2, psi B becomes 1. This is the state A, this is the state B. Initially the number 1 level particle is in the state A and number 2 particle is in the state B, and after some excitement or some exchange, this is the exchange. After exchange the particles, which particle will be where? This is the particle 2 and this is the particle 1. They were exchanged. Okay, they are exchanged. Okay, therefore the wave function will be what? Here the wave function was psi A 1. This means the number 1 particle was in the state A, and in the second case what will happen here? The number 2 particle will be in the state A. Okay, this is the exchange. Okay, now minus what will happen here? Here psi A2, this means it will become psi A1, psi B2. The wave function completely flipped up. Now take a minus sign out from this bracket. What will become? 1 upon root 2 psi. This term will come on the first, psi A1, psi B2 minus psi A2, psi B1. Just wait for a while. Okay. Except the negative sign here. Let me. What is this? Okay. Sorry. Except the negative sign here, the rest of the wave function is similar to negative sign here. Psi total 1 2 state. You can check it out. Okay. What was there? This is the wave function. And this wave function is like this. This means psi 2 1, psi total 2 1 becomes minus psi total 1 2. This is the property. This is a important property of Fermi exchange. Okay, Fermi particle exchange. Under Fermi particle exchange, we get a negative sign here. This is the antisymmetric wave property. We know what is an antisymmetric wave property. That inverting the space. Okay, Say something, a function. Say a function x is written like this. Is written like x cube. Suppose an antisymmetric function. If this is antisymmetric, then this is antisymmetric or not? Let's check. Put minus x in the place of x. Then what will happen here? F of minus x. This means minus x to the power cube. Completely replace the x by minus x. This gives what? This becomes minus x cube, this means minus f of x, because f of x was only x cube, minus fx, this means f of minus x is equals to minus f of x. This is called the antisymmetric function. Similar thing happens in case of the wave function of Fermi particles. Okay, is it clear? Please comment on the comment box, and if you going through this lecture, please share among your friends and subscribe the channel. Okay, I have seen that 50% of the students are watching the videos but not subscribing the channel. Please subscribe the channel. Okay. Okay, this was the Fermi particles. In case of bosons, let me write in case of bosons. The above discussions was of Fermi particles. In case of bosons, what will happen here? The total wave function in case of bosons is given as psi total of particle 1 and 2, 1 upon root 2 psi a1 psi b2 initially. Here comes a plus sign, which is not for the case of Fermi particles. Okay, here what happens? Psi a2 and psi b1. This one is the total wave function of the particles when the number one particle is in the state A and number 2 particle is in the state B. Under exchanging this particle, if you exchange this particle, state remains same, but the particle 2 comes here, particle 1 comes here. Okay, this means that the psi total becomes what? Psi total 2 1. This becomes what? 1 upon root 2 psi a. Here comes the 2 psi b. Psi b 1 plus psi a 1 and psi b 2. Let's reorganize this above equation as drag the second term in the first place, psi a 1, as there is no negative sign. In case of fermions, we have seen that there was a negative sign when we can take the negative sign out of the box and this becomes antisymmetric. In this case, there is no negative sign and hence we cannot drag any kind of sign out of the box. Okay, this means psi a to psi b. We have no way to organize these states. Okay, this means this is what, this is our psi total in case of 1 2. This means what? Before exchange, this is in the case of before exchange this comes, and this is in the case of, this one means this. Okay, this is in the case of after exchange. Look at this closely, that the psi total 1 comma 2 becomes psi total 2 comma 1. This is quite significant that under exchanging the particles, the wave functions do not changes. Okay, this is a important property of bosons. Okay, sometimes these questions come directly from the concepts. Okay, so this was the lecture of distinguishable particles, indistinguishable particles, and bosons and fermions, or bosons or fermions. Okay, this is, now the lecture will become so long, so I have to stop it. Okay, thank you. and on the next lecture we will discuss about some other topics, say the non-interacting particles thermodynamic limit. Okay, in this case, okay, macro step micro steps are remaining. Okay, thank you.